My name is Yuan Meng. I am a PhD student at the University of Southern California. I'm presenting the paper DYNAMAP, Dynamic Algorithm Mapping Framework for Low Latency CNN Inference. Convolutional neural networks, or CNNs, have shown great breakthrough over the recent years, and is applied in many applications that involves image classification and object detection. Here we show the milestones and revolutions of CNN architecture in the past 10 years, and the explosive bloomings of new CNN architectures, as well as new techniques. Looking at the size of each circle that represents size of a milestone network architecture, we have seen that overall trend is CNNs are getting larger and more powerful over the years. With the ever so stringent requirement on low latency, some more compact networks are also designed along with new types of convolution layers. Recent CNN architectures have shown more diverse kinds of layers in the same network, such as network with narrowly shaped kernels in the inception families, pointwise and depthwise convolution in MobileNet, etc. These networks are also adopting more complex CNN graphs involving branchings and merging edges such as inception, open pose, and efficient data networks. Moreover, with the rising of CNN, we also witness various algorithms to perform 2D convolution operations, such as the image-to-column method, the frequency domain convolution method, the Winograd fast convolution method, and the low memory kernel-to-row method. With all these variations, how can we deploy a unified strategy to optimize the inference latency of any given CNNs, no matter what network architecture it has? Most real-world applications require blazingly fast inference time, varying anywhere from a few milliseconds to 1 second. For example, autonomous driving vehicles requires as low as milliseconds of inference latency for immediate response to the environment, and now smartphones use Face IDs to unlock. The user doesn't want to wait for more than 1 second every time before they can use their phone. Therefore, the objective of our work is to minimize inference latency of single image inference. With the blooming new evolutions in convolution operations and techniques, here comes new challenges in optimizing inferencing latency when accelerating CNN on FPGAs. To avoid expensive runtime reconfiguration which could hurt latency, most existing FPGA-based solutions usually use a specific algorithm across all the layers and reuse a generic architecture to deploy the algorithm. However, this may not be efficient for some of the emerging networks which have more diverse layer shapes and complex structures, so different layers have different bottlenecks in terms of memory and computation. If one wants to use a one-size-fits-all strategy, it may result in suboptimal latency. Figure 1 here shows 3 common layer configurations that uses only different kernel sizes. The computation and memory overheads of using 3 popular algorithms are largely different from each other, and the optimal algorithm therefore are different for each layer. Therefore, we propose to deploy different algorithms targeting different layers to fully optimize inference latency. However, this proposal leads to some new problems. One major problem that comes into the picture is how can we quickly identify an optimal algorithm configuration from the vast number of mapping choices that occur on a deep network. We choose 3 commonly used generic matrix multiplication-based convolution algorithms as our target. The major reason is that they all map to some GEMM tensor operations, and there is an opportunity to develop a unified architecture to accelerate them without expensive runtime reconfiguration. Even with only 3 algorithm choices at each layer, the algorithm mapping space increases exponentially with respect to the number of layers in a network. For example, we take GoogleNet, which has 22 convolution layers in total. This gives us over 30 billion mapping choices. How can we fastly identify the best choice? The other major problem to answer is CNN graphs are getting more complex with all kinds of branching and merging edges in their graphs. If we switch algorithm between layers, there are some unavoidable extra overhead coming into picture because different algorithms require different feature map layouts to efficiently perform on a certain convolution layer. When we switch algorithms between adjacent layers, the data layout transformation and extra data communication costs are unavoidable. So based on the complex layer connections, how can we efficiently decide what algorithm is best for each layer, and whether the performance gain from switching algorithm for the next layer can override the extra overhead we pay for it? We first explain our formulation of the algorithm mapping problem. We assume a CNN graph is known with a set of vertices representing layers, a set of edges representing the ordering between layers. Each vertex is associated with a cost vector C, whose entries are the computation cost of performing a specific algorithm on the current layer. Each edge is associated with a transition cost matrix T, where each entry A sub 1, A sub 2 denotes the transition cost of switching between algorithm 1 and 2 between the two layers connected by the edge. The diagonal entries are the cost of using the same algorithm between two layers. The transition cost is composed of all data communication and data layout transformation cost between the two layers. For layers connected with two edges, we use a split node notation in the cost vector construction. The detailed graph construction description can be found in our paper. At each layer, apart from the algorithm cost vector C, we also define an assignment vector X, where the kth entry of X is 1 only if algorithm K is selected at the current layer. This way, we mathematically formulate the optimization problem as the sum of all computation costs at all layers and the sum of all transition costs between all layers, where the computation costs are gained by dot product between the assignment vector and the cost vector at each vertex, and transition costs are obtained by multiplying the transition cost matrix on each edge with the two assignment vectors of its two adjacent layers as shown in the equation. This formulation is known as the partitioned Boolean quadratic programming problem, or PBQP. PBQP has been widely used to model a number of compiler optimization problems such as register allocation with irregular instruction sets and instruction selection on directed acyclic graphs. PBQP is NP-complete in general. However, we show that for a class of graphs known as a series parallel graph, PBQP can be solved in polynomial time by applying iterative graph reduction. Moreover, we show that the graphs of a majority of popular CNN architectures fall into this class. This allows us to develop a polynomial time optimal algorithm for the algorithm mapping optimization problem defined above. If you're interested, you can check out the detailed proof for optimality uploaded to arXiv. The accelerator is composed of a core computing unit performing matrix multiplication, linear transform modules for Winograd, a pad and accumulation module for kernel-to-row algorithm, data layout transformation modules for data reordering when switching between different layers and algorithms, and a pooling module for max pooling on spatial feature maps. The core computing unit is a configurable sized 2D symbolic array composed of multiply accumulation units optimized for generic matrix multiplication. The input buffer and kernel buffer are organized into a number of banks inconsistent with the two systolic array dimensions. Each bank stores a partition of the input feature matrix or kernel matrix. During the GEMM execution, data are read concurrently by parallel PEs in the systolic array, PE meaning the processing element, and data are written to multiple banks of output buffer in parallel. Under different algorithm modes, our control unit switches between different data paths in the auxiliary modules around the systolic array. For example, under Winograd algorithm mode, input and outputs go through the linear transformation modules, and under kernel-to-row algorithm, the systolic array produces intermediate output features from multiple one-by-one kernels, one-by-one subkernels, which are then stored and accumulated in the pattern and accumulation module. We applied multiple hardware optimizations in this overlay to further optimize inference latency under generic matrix multiplication calls. First of all, we developed a compound processing element in the systolic array to support both output stationary and wait stationary data flows to drive up effective PE utilization in the systolic array. Furthermore, since different data flows require different memory access order, we support fast data access in both data flows by storing the kernels in the buffers in a shifted blocked layout so that PEs in the systolic array can access kernel data in both normal order and transposed order. Lastly, we designed the layout transformation units to achieve layout transformation on the fly with minimal overheads when switching between algorithms between layers, which adopts parallel finite state machines to output the desired DDR addresses that are going to be fed into the memory controller. Now we show the DYNAMAP framework execution flow. DYNAMAP uses a hardware overlay template which is parameterized with the systolic array dimensions, sequence of optimal data flows, and sequence of control signals encoded by specific algorithm mapping that defines the behavior of various auxiliary modules such as data layout transformation, linear transformation, pattern accumulate. As shown in Figure 6, after FPGA device capabilities and CNN metadata inputs are provided, DYNAMAP executes the following steps. 1. Hardware customization performs design space exploration to identify systolic array dimension and best data flow associated with all available algorithms in each layer. 2. These hardware parameters are used together with CNN metadata in the computation and transition latency performance models, which are used to construct and populate the CNN graph. 3. An off-the-shelf PBQP solver is utilized to perform the node reduction steps for algorithm mapping. The PBQP solver outputs the optimal algorithm assignment vectors for all layers. 4. Based on the algorithm data flow mappings, the template overlay is customized. 5. CNN is scanned to identify if the total memory consumption exceeds on-chip SRAM capability. Thus, when accelerating smaller networks on FPGA devices with larger on-chip memory, redundant off-chip data traffic will be avoided by configuring layout transformation modules to generate on-chip memory addresses. 6. Integrating all the optimizations, control signal sequences are generated to support the algorithm and data flow switching on the hardware overlay. The output of DYNAMAP is synthesizable Verilog program to be deployed on the target FPGA device. We use Xilinx Avio U200 FPGA board to evaluate the designs generated by our framework. We use 8-bit fixed-point data representation to perform CNN inference. We generate the hardware algorithm code designs for two CNNs, GoogleNet and Inception before. For GoogleNet, the framework generated a 92x66 systolic array, and we show the different layer-wise latency breakdown for inference on this accelerator. In this chart, on the x-axis, we group all the convolution layers in each Inception modules consistent with the notions in the original GoogleNet publication. Corresponding columns show the sum of computation and communication latency of all layers in an Inception module. The into-code only and kernel-to-row applied columns show the results of using one algorithm across all the layers, and the window applied columns show the results of applying Winograd algorithm wherever applicable and into-code everywhere else. The OPT returned are the results using algorithm mapping returned by DYNAMAP, which is observed to have the most superior performance among all the columns. It's interesting to note that switching to kernel to row is not always better than directly using into-code. This is because GoogleNet has a lot of 1x1 layers and square-shaped kernels, which are compute-bound, where kernel to row either does not have any benefits or have some small benefits which cannot offset the overheads due to pattern accumulate, making it less advantageous. Winograd, on the other hand, reduces the amount of computations and the extra overhead is worth paying for the overall performance gain in layers with square kernels, which dominates a lot of inception modules. For Inception v4, the framework generated a 95 × 64 Satoshi array, and we show on this accelerator the different layer-wise breakdown for inference latency. In the chart, we see the same trend as on GoogleNet, that is, the OPT algorithm mapping is better than naively using any algorithm alone. In Inception v4, a large portion of the kernels are shaped 7x1 or 3x1, making such layers more memory bound. Therefore, in this chart, we see the low memory algorithm kernel to row almost always outperform into-code, which requires data duplication. While applying Winograd on square kernel layers always reduces the computation complexity, it's not always optimal overall. This is because for kernels larger than 3x3, multiple rounds of 3x3 Winograd is required, resulting in severe transformation overheads and amortized decrease in computation complexity reduction. Winograd also imposes high memory overhead and layout transformation cost, so sometimes kernel to row is overall better for such layers with slightly higher computation costs but significantly lower communication overhead. This table compares the performance of our design produced by DYNAMAP with existing works accelerating the same networks or similar networks. We achieve 286 MHz frequency for both GoogleNet and Inception v4. GoogleNet acceleration using DYNAMAP significantly outperforms number 12 and 28 in terms of both latency and throughput. This is partly due to the advantage of DYNAMAP's optimizations on data flow and algorithm switching, and partly due to the lower precision adopted, enabling more processing elements. The motivation of number 19 is similar to that of DYNAMAP. However, it uses dynamic tiling with data layout optimizations across different layers to drive up effective DSP utilization in the Satoshi array. They experimented on a different network with higher precision, but if we scale their best case performance to GoogleNet and Inception v4, assuming the same number of PE to support floating point computation, DYNAMAP achieves lower latency because the use of compute reducing and memory reducing algorithms. For Inception v4, we compare with 32, which applies dynamic memory management to overcome data transfer bottlenecks, and 26 that uses kernel to row method for all layers in GoogleNet. Compared to 26, even with lower frequency, our design achieves 20% speed up. While using Winograd on some layers leads to low complexity, its impact is limited as there are more memory bound than computation bound layers in Inception v4. As future CNNs evolve to be more layer device and the trade-offs become less obvious, then the benefits of using DYNAMAP will become much more pronounced. In conclusion, in this paper, we developed a unified template hardware overlay reused across layers with the ability to perform algorithm switching and data flow optimization, and we developed the DYNAMAP automation framework that supports polynomial time algorithm mapping through PPQP and efficient hardware mapping. Thank you for listening.